Hi and welcome to video 6 on definite integrals and the area below curves. And in this video I'm going to talk to you a little bit about some further examples that you might see. And this doesn't cover everything, but it certainly go a long way to covering some of the types of questions that you may receive, maybe in a complex familiar or complex unfamiliar case. So let's look at 3 examples. First of all, example 9. By first deriving log x squared plus 2, determine the area bounded by the x-axis, curve y equals x over x squared plus 2, and x equals 1 and negative 1. So the first thing I'm going to do here is recognize that this is a question a little bit like we've done in normal indefinite integration before, where we're asked to derive something first. So in all likeliness, when we integrate this thing, it's probably going to come out looking similar to, maybe just a constant multiple of, the thing that we get to derive. So the question is really leading us in what to do. So we'll get to the derivative first. What I want to do is set up my integration now that I've read the question, I'm embedded in that process. So my integration is going to look like this. I'm going to integrate x over x squared plus 2 with respect to x, and I'm going to integrate it between 1 and negative 1. My issue is I don't know what the integral of x over x squared plus 2 is, but I can see it's a f of x in the denominator with the derivative f dash of x in the numerator. So it is going to look like a log. That's kind of what I'm expecting. So let's go here on the side and let's do that suggested derivative. So if I derive the natural log of x squared plus 2, this of course is equal to 1 over x squared plus 2. That's how we derive log. 1 over the thing on the inside of the log. And we have to multiply by the derivative of the inside, which is 2x, and the plus 2 contributes nothing. And so the answer is 2x over x squared plus 2. And so what that tells me is that the derivative, d dx, of log x squared plus 2 is equal to 2x over x squared plus 2, which in turn tells me that if I integrate both sides like this, I get just log x squared plus 2 equals the integral of 2x over x squared plus 2 dx. And in fact, because I'm integrating this thing over here, which doesn't have a 2x, what I'm going to do is I'm going to divide both sides by 2, and it gives me a half log x squared plus 2 equals the integral of x over x squared plus 2 dx. So now we can see that it looks like what we're trying to integrate in the other section. So we can go and use this now in our integral. So I'll just rub this out, and we know now that this is equal to the natural log of x squared plus 2 between 1 and negative 1, but of course there's a half there, because once we've done our final calculation down the bottom here, we had that half. And so we've got that substitution now, and of course we can now just substitute those things straight in. A half log 1 squared plus 2 minus a half log negative 1 squared plus 2. And this is a little bit of a problem, because I can see here that we're going to come out with a half log 3 minus a half log 3, which of course is equal to 0. So it's going to be beneficial for us now to plot this graph on our graphics calculator and have a look at what it looks like. And so I've chosen to do this in the Casio to show you what it looks like. Here's the function I've typed in. I'm investigating the look of this function. And what I'm going to do now is just quickly sneak into the V window. I've already set this up, but in the V window, I want to do an integral between negative 1 and 1. So of course I'm going to look at negative 1.5 to 1.5. That gives me the opportunity to see every aspect I need to. And I did a little bit of calculating about what y would be equal to, and negative 1 to 1 was going to be fine there. But you could just trial and error that a little bit as well. If I draw that, there's my graph. And so I've copied that graph and I'll paste it here. And now it's this is the point where I recognize that I have got an issue, and that is that the graph crosses the axis at 0, and so therefore I'm going to have a look at my integral differently. So I've done a bit of work, and that's fine. It's really good for you to see how you can build an answer to a question, particularly if you go the wrong way a little bit. And how also just to recognize that you've possibly made a mistake, like getting an area of 0, for example. So I'm going to calculate the integral from 0 to -1 of x over x squared plus 2 dx. And then I'm going to add to that the integral from 1 to 0 of x over x squared plus 2 dx. But I'm going to recognize that this integral here, this area, that is negative, so I'm going to make it negative here. And so that gives me negative of, bracket here, a half natural log of x squared plus 2 between 0 and -1 plus a half natural log x squared plus 2 between 1 and 0. And of course, I now get the situation where the half is a common factor, so I'm going to take the half out. And I've got negative of, there's going to be a lot of brackets here, but I'm going to be really careful. In fact, I've got one term each, so that's okay. Log, I'll put in 0 first, which just gives me log of 2, minus -1 gives me log of 3, and then I add to that log of 3, put in the 1 first, minus log of 2, and of course this is equal to a half. I've got positive log of 3 twice, so I've got 2 log 3 and then minus 2 log 2, and I can do some simplifying here, so let's just be a little bit careful. First of all, the halves work out quite nicely, so I get log 3 minus log 2, and then I can do log of 3 over 2, and that's my exact value. I'm going to leave it as that. You can calculate that at 2 decimal point, but really in math methods it's time for us to start working exact values unless we're told otherwise. So there's our solution, and we've got a graph to back it up so that we know that our solution is reasonable and makes sense, whereas the 0 was unreasonable.